Welcome, everyone, and thank you for being here today. I'm excited to introduce our topic, Fundamentals of Scientific Study, covering variables, measurement, and analysis. On this first slide, you'll see the title and subtitle, giving us a quick overview of what we'll explore. Over the course of this presentation, we'll dive into the core concepts of experimental design, how we collect data, and the ways we validate our findings. So, let's get started and uncover the essentials that form the foundation of scientific research. Welcome to our discussion on the fundamentals of scientific study. Today, we'll explore key concepts like variables, measurement, and analysis that form the backbone of scientific research. Let's start with variables. In any scientific study, variables are the elements that can change or vary, and understanding them is crucial because they influence the outcomes of experiments. There are different types of variables we need to be familiar with. Independent variables are the ones we manipulate or change to see how they affect other factors. Dependent variables are the results or responses that we measure, which depend on the independent variables. Controlled variables, on the other hand, are kept constant to ensure that the experiment remains fair and that the results are due to the factors we're specifically testing. Moving on to measurement and units. These are essential for quantifying variables accurately. We distinguish between fundamental quantities, like length or mass, and derived quantities, such as speed or density, which are calculated from fundamental ones. Correspondingly, we have fundamental units, like meters or kilograms, and derived units, like meters per second or grams per cubic centimeter. Understanding the differences between these units and quantities helps us maintain consistency and accuracy in our measurements. This is where the principle of homogeneity comes into play, ensuring that all quantities in an equation are expressed in compatible units to avoid errors. By grasping these core concepts, variables, measurement, and units, we lay a solid foundation for conducting precise and reliable scientific studies. These tools enable us to analyze data effectively and draw meaningful conclusions from our experiments. Now, let's look at the fundamentals of scientific study, focusing on variables, measurement, and analysis. On this slide, we'll walk through the key steps involved in conducting scientific research. First up is observation. Every study begins with observing natural phenomena, simply noticing and describing what we see around us. This step sets the stage for everything that follows. Next, we move to hypothesis formation. This is where we propose an explanation for the phenomena we've observed. Think of it as making an educated guess about what's happening and why. Once we have our hypothesis, we design and perform experiments. This is experimentation. It's about creating controlled tests to see if our ideas hold true. After conducting experiments, we gather data. This is data collection. Collecting accurate information from our observations and tests is essential because it provides the basis for analysis. Finally, the analysis step involves interpreting all the data we've collected. This is where we make sense of the results, understand what they tell us, and draw meaningful conclusions. Together, these steps form the core process of scientific study, helping us uncover truths about the natural world through careful measurement and analysis. Let's talk about the fundamentals of scientific study, focusing on variables, measurement, and analysis. On this slide, we'll explore what variables are and why they are so important in experiments. Variables are essentially the factors, traits, or conditions that we consider and manipulate during our research. They help us analyze and interpret data effectively, making our findings more meaningful. For example, if we change the length of a rectangle to see how it affects the area, the length is our variable. Similarly, varying the temperature to observe how it influences solubility is another common example. These variables are crucial because they allow us to test hypotheses and understand relationships within our experiments. Understanding variables is key to obtaining accurate and reliable results. They are central to designing experiments that can yield valid conclusions. So, in essence, variables are the building blocks that help us explore scientific questions in a structured and meaningful way. Now, let's dive into the fundamentals of scientific study, focusing on variables, measurement, and analysis. First, we see that variables are things changed by the experimenter, and they are also the cause of the effect we observe. They play a crucial role in determining outcomes because they help us understand what influences what. Variables serve as the basis for scientific manipulation, meaning we adjust or control them to see how they impact our results. Moving on, we have different types of variables, each with its own role. Independent variables are those that respond to changes we make. They are the ones we manipulate or vary intentionally, and the effects we observe are called the dependent variables. Essentially, the dependent variables reflect the impact of the changes we introduce through the independent variables. It's important to remember that the independent variable is what we control to see how it affects the dependent variable, which measures the outcome. This clear distinction helps us design experiments effectively and interpret our results accurately. By understanding these relationships, we can better grasp how experiments reveal cause and effect connections, which is at the heart of scientific investigation. Now let's talk about independent variables, which are a fundamental part of scientific studies. When we look at graphs, you'll notice that independent variables are typically plotted on the x-axis, or the horizontal axis. This placement makes it easier to see how changes in the independent variable relate to other variables on the y-axis, helping us visualize their relationship clearly. So, what exactly are independent variables? They are the ones that the scientist changes freely during an experiment. Think of them as the cause or input we're testing to see how they influence the outcome. Because they are deliberately manipulated, they play a crucial role in determining what results we observe. This is why selecting the right independent variable is so important. Focusing on a single, well-chosen variable allows us to interpret our data more clearly and understand the cause-effect relationship we're investigating. It keeps the experiment straightforward and ensures that our conclusions are valid. In the context of the overall study, understanding and properly managing independent variables helps us uncover meaningful insights about the phenomena we're exploring. Let's take a closer look at dependent variables. These are crucial in experiments because they help us understand the impact of the independent variables we manipulate. Essentially, they show us the outcomes or responses that depend on what we change in the experiment. Now, measuring these dependent variables accurately is really important. Precise measurement ensures that our conclusions are valid and reliable, giving us confidence in the results we observe. When we visualize data, dependent variables are typically plotted on the y-axis, which is the vertical axis of a graph. This placement makes it easier to see the relationship between the independent and dependent variables at a glance. To define dependent variables simply, they are the responses we observe that depend on the independent variable. In other words, the effects or outputs of our experiment. Understanding this helps us interpret the results correctly and understand how the independent variable influences the outcome. Let's talk about controlled variables and their role in scientific studies. Controlled variables are essential because they impact the accuracy of our experiments. By keeping certain factors constant, we make sure that any changes we observe are truly due to the variable we're testing. This helps us trust our results more. The main purpose of controlling variables is to ensure that the experiment is testing only the relationship we're interested in, without interference from external factors. For example, if we're studying how pressure affects a reaction, we might keep the temperature constant to avoid it influencing the outcome. Or, if we're changing sugar concentration in a solution, we keep the amount of water the same to isolate the effect of sugar. Controlled variables are simply factors that we keep steady throughout the experiment. They prevent confounding effects, which are those unwanted influences that can lead us to false conclusions. Overall, controlling variables is about maintaining consistency so that our results are accurate and reliable, helping us draw valid conclusions from our scientific investigations. Now let's talk about measurement and units, which are fundamental to scientific study. The International System of Units, or SI, is used worldwide to ensure consistency across different fields and countries. This standardized system acts as the global framework for all measurements we make in science. When we adopt SI units, it allows us to communicate our findings clearly and reliably, no matter where we are. Accurate measurement and proper use of units are essential because they form the backbone of scientific inquiry. They enable us to perform precise experiments and trust the results we obtain. Think of units as a common language for expressing quantities. They make our scientific communication clear and consistent. Measurement itself is the process of comparing an unknown quantity to a standard unit. It's such a basic yet vital part of science, helping us quantify and understand the world around us. Without proper measurement and units, our scientific conclusions wouldn't hold the same weight or clarity. Fundamental quantities are the basic building blocks of all scientific measurement. They are independent, meaning they cannot be derived from other quantities, and they form the foundation for understanding the physical world. Examples include length, mass, time, electric current, temperature, luminous intensity, and the amount of substance. These quantities are universally recognized and standardized, ensuring consistency across scientific studies. Moving on, we have fundamental versus derived quantities. Fundamental quantities, as I just explained, are the starting points. Derived quantities, on the other hand, depend on these fundamental quantities. For example, velocity is derived by dividing length by time. Force is calculated by multiplying mass by acceleration, and pressure involves force over area. These relationships allow us to calculate more complex measurements, providing deeper insights into physical phenomena. They are essential for advanced scientific analysis, helping us understand how different aspects of the physical world connect and interact. Let's take a closer look at the fundamentals of scientific study, focusing on variables, measurement, and analysis. On this slide, we're emphasizing the importance of fundamental units. These units correspond to fundamental quantities and are independent of each other. For example, we have the meter, symbolized as m, which measures length, the kilogram, or kg, for mass, the second, s, for time, and the ampere, A, for electric current. These units are the building blocks for all other measurements we perform in science. They are essential because they help us define physical quantities in their simplest form, making our measurements precise and consistent. Now, moving on to the difference between fundamental and derived units. Fundamental units, as we've discussed, are the basic units based on fundamental quantities. Derived units, on the other hand, are combinations of these fundamental units. For example, a newton, which is the unit of force, can be expressed as kg meter second squared. A pascal, used for pressure, is newtons per meter squared, and a joule, which measures energy, is newtons per meter squared. These derived units allow us to express more complex physical relationships in a standardized way. Understanding these derived units is crucial because it helps us with dimensional analysis and solving problems more effectively. It's all about building a comprehensive framework that allows us to interpret and analyze physical phenomena accurately. So, in summary, fundamental units are the core building blocks, and derived units are the combinations that help us describe more complex concepts in physics. Now, let's move on to the fundamental concept of homogeneity in scientific study. The principle of homogeneity states that all terms in a valid equation must have the same units. This is a crucial rule because it helps us ensure that our equations are physically correct. If the units don't match, the equation simply doesn't make sense in the real world. The purpose of unit analysis is to check whether our physical equations are dimensionally consistent. Essentially, it's a way to verify that the equations align properly with the physical dimensions involved. This step is important because it helps us catch errors early before we even start experimenting. In practical terms, this method serves as a quick and effective way to verify the correctness of equations. It acts as a preliminary check, saving us time and preventing mistakes in calculations related to physical quantities. Let's look at an example to see how this works. Consider the equation v equals u plus at, where v is velocity, u is initial velocity, a is acceleration, and t is time. The units of velocity must match the units of acceleration multiplied by time. If they don't, the equation isn't dimensionally consistent, and that indicates something's off. This illustrates the importance of the principle of homogeneity. By checking units, we ensure our equations are valid and reliable, forming a solid foundation for all our physical calculations and analyses. Now, let's discuss some applications and limitations of unit-wise analysis. First, it's important to recognize that unit analysis does not distinguish between scalar and vector quantities. This means that while it's a powerful tool for many calculations, it doesn't tell us if a quantity has direction or not. being aware of this limitation is crucial for accurate scientific interpretation. Next, we should remember that unit analysis cannot reveal numerical constants or coefficients in equations. These constants often carry significant information, so we need to consider this limitation when analyzing data or formulating equations. Another key application of unit analysis is unit conversion. It's a handy method to convert between different measurement units, ensuring our calculations are consistent and accurate across various systems. Finally, unit analysis is also useful for verification and understanding. It helps us check if an equation makes sense by ensuring that units are consistent on both sides. Plus, it aids in understanding the relationships between different quantities, reinforcing the overall insight into the physical phenomena we're studying. So, while unit-wise analysis is an invaluable tool, keeping these limitations in mind ensures we use it effectively within the broader context of scientific investigation. In conclusion, understanding the fundamentals of variables, measurement, and analysis is absolutely essential for conducting meaningful and reliable scientific studies. Mastering these concepts helps us ensure that our results are credible and reproducible. One key tool I want to highlight is unit analysis. It's a powerful method for validating physical equations because it allows us to check whether our calculations make sense by verifying the units involved. This process is crucial for confirming the correctness of scientific computations. Next, measurement with standardized units plays a vital role in maintaining accuracy and enabling comparison across different experiments and studies. Using consistent units ensures that everyone is on the same page and that our data is reliable. And at the heart of experimental design are variables, specifically independent, dependent, and controlled variables. These are the building blocks that help us structure our investigations and interpret the outcomes effectively. So mastering these principles, unit analysis, standardized measurement, and the understanding of variables is fundamental to achieving scientific accuracy and integrity in our work.